3.3. Recursion tree for merge sort. In this part, we will use two methods to get the general case, worst case merge sort estimate. Yeah. Two methods. Yeah. One, recursion tree method. We draw recursion tree. Yeah. So we did that before. Yeah. Another, apply smoothness rule theorem. We have that theorem. Yeah. But we have not used that much. So we are not quite familiar with smoothness rule. So in this example, so we have a chance to apply it. Yeah, it's a good example using smoothness rule. Yeah. So let's look at that. So now to solve this recurrence relation, but this time we do not assume n equals power of 2. N is not necessary power of 2. N is the general case. Yeah. So we want to extend our result from special case to the general case. Yeah. So how to do it? Yeah. Recursion tree method is a simple, effective estimation method. We do not need to do a lot of math. So using that tree, so we can get a structure. All right. After we understand the structure, we can estimate the total cost, solving the problem with a very good approximation. Yeah. So let's do it. So when we start, using this recurrence equation, we can draw that tree. Okay? Yeah. The original function we put at the root. Yeah. In order to solve this problem, we need to solve two smaller subproblems. So we split it. Yeah. This node, the root node, we can split it into two branches. Yeah. Two subproblems. Each one, the cost is, so we put as the node, as the child nodes. Yeah. All right. But at the same time, we want to represent the non-recurrence cost. Non-recurrence terms, also we use a corresponding binary tree to organize the non-recursion cost. At the root, non-recursion cost for corresponding to T of n. Then two child nodes, corresponding non-recursion cost for that particular recursive function call. Okay, all right. So with that structure, so we go down all the way until we, reach some level. Okay, yeah. If we go to the bottom level, so you can see, so we try to figure out how many levels do we have. We want to estimate that level number. Yeah. All right. So given n greater or equal to 2, we can do this. There exists an integer k such that this n is between 2 to the kth and 2 to the k plus 1. We can always find such k, right? Yeah. Between, in other words, any integer, any positive integer greater than 2, we can always find two adjacent power of 2 to cover this integer. Two adjacent, so here we find an interval. the left endpoint of the interval 2 to the k, the right endpoint 2 to the k plus 1. So this interval covers n. So n must be inside this interval. That's the meaning. Okay? All right. Yeah, it's easy to see that. Yeah. So we do not need more steps for the proof. Yeah, we can see that easily. Yeah. In that way, if we take log base 2, we can get this relationship. Yeah. So the k between log of n and the log of n minus 1. Okay? Yeah. So then we estimate the number of levels. The number of levels, k plus 1. K plus 1. Okay? Yeah. Yeah. Also, 2 places we have k plus 1 levels. And the cost. So here you can see each level, the cost is n. Next level, you add up these 2, you also get n. Next level, you add up all the terms, you also get n. Right? So each level you have cost n. You have log n levels, right? You have log n, approximately log n levels. So the total cost approximately big theta of n log n. Okay, yeah. So we find the answer. Yeah, that is for the general n. That is for the general n, not the special n. Okay? But it is the estimate. When we do this, it is an estimate. Yeah. But you can see this estimate is pretty close. Yeah, it's a good estimation. Yeah. All right. But the next, I want to use the smoothness rule to get the same thing. Yeah, here. I want to use the smoothness rule to get the same result, but using different tool. RecursionTree is one tool. Smoothness rule is another tool to solve the same problem. Yeah, so let's see smoothness rule. First, let's recall that smoothness rule a little bit. So what is the smoothness rule? Yeah. So I just copied from the notes. Yeah. 3.b, module 3, part B. Yeah. So we just get a smoothness rule from there. Yeah. Let t of n be an eventually non-decreasing function, and f of n be a smooth function. Okay. Yeah, smooth function, I will talk about that a little later. So we get this rule first. If t of n belongs to big theta of f of n for values of n that are power of b greater or equal to 2. Yeah. In our case, our b equals 2. Our b equals 2. Power of 2, yeah. So we have a special result for power of 2. So power of b, yeah. From there, the conclusion, t of n belongs to theta of f of n for the general n. Okay? So if the special case is true, we can get a general case. General case also true if it is a smooth function. What is the smooth function? Yeah. Some of you may get confused with the calculus smooth function. In calculus, when we talk about smooth function, the curve must be smooth. That's the smooth function, right? So the derivative is continuous. So basically the derivative is continuous. So then we say smooth function, right? Yeah. But here we do not mean that. We do not mean that. So if you draw the curve, you look at the shape, it is smooth. We do not mean that. Our smooth function is different. Our smooth function has a key smoothness condition. So that is f of 2n belongs to big theta of f of n. Big theta of f of n. Okay? Yeah. So that's the key condition. Yeah. All right. So next, we can check our f of n is smooth or not based on this condition. Okay? Our f of n equals n log n, n times log n. Now let's take a look. Do we have this condition? If we have, it is smooth, so we can apply the smoothness rule. Okay? All right. So let's look at f of 2n. What is that? 2n times log base 2, all right? Log base 2, 2n. Okay? All right. So now we simplify a little bit. Still 2n, but that one we can write log base 2 of n plus 1, right? Yeah. Okay. This 2 constant, remember some constant multiply that function. This one minor term, very small, we can ignore, right? So you can see this function is still belongs to big theta of n log n, right? This condition is satisfied. Then we can say this function is smooth. Okay? If it is smooth, we can apply the smoothness rule. We know it is eventually non-decreasing, right? Yeah, this function eventually non-decreasing. Yeah. And we know our theorem T of n is true for power of 2, right? We know power of 2. Then for the general case, T of n belongs to big theta of this function. How about that? Okay? So that's the power of smoothness rule. That's the power. Yeah. You know, non-trivial. Yeah. This result, non-trivial. Yeah. But when we apply this theorem, we can quickly get this result. Otherwise, you need to do a lot of work. Okay? Yeah. All right, so we complete this solution. Yeah. Now we can see for the worst case, the merge sort, we can get big theta of n log n efficiency. Now we have this. Yeah. So the best case, average case, only better than this one. The worst case already this good. So the best case, average case can only be better than this. Yeah. But even better than this, here, let me tell you. Yeah. So even for the best case, average case also belong to big theta of n log n. Okay? Yeah. In other words, worst case, best case, average case, all three cases all belong to big theta of n log n. Because it is a very balanced data distribution, right? Balanced data distribution, so the best case, worst case, very close. Pretty close. Yeah. All right. So here we do not prove that, yeah, because the proof could be very long, yeah, not easy. Yeah. So I just, make comments on that. Yeah. The last thing of this video I want to look at from divide and conquer view. Yeah. So we solved the sorting problem, the merge sort, but let us use the divide and conquer view to understand our method. Yeah. Divide and conquer view, we have 3 steps. The first step, divide step. Divide step for the merge sort. How much cost do we need to pay? Divide step. We chop the array right in the middle. That's very easy. So the cost is very low. specifically big theta of 1. So you do the split, big theta of 1. So easy. So we find a midpoint, and from there, we call recursive functions on 2 subarrays. The conquer step, just a recursion. We do not need to do any specific work, just call our original cost function recursively. So that's automatic. Okay. Then combine step. The combine 2 sorted subarrays, that's the merge step. What is the cost of the merge step? Okay. Depends on your data size. Suppose this is your data size, K. K is your data size. Then the cost, big theta of K. Relatively high cost, relatively high comparing with this low one, big theta of 1, relatively high cost. Okay. So in this way, we try to understand from the divide and conquer view. Because you cannot make these both steps low cost. It's impossible. It's a trade-off thing. If one step, usually the conquer step recursion, so we can skip it. We can ignore it. So we only look at the divide step and the conquer step, combine step. So you cannot make both steps low cost. Okay, it's a trade-off thing. If you make one step low cost, the other step you need to pay relatively high cost. Okay, or conversely, combine step low, but divide step high, relatively high cost. Okay, so that's the view using divide and conquer. All right, so we stop this video and complete the whole class.